Okay, so today in this pre-reading for Exploration 541, we're going to have some information on the derivative, which you'll definitely do much more in calculus if you take calculus. But here is our beginning investigation of it. So you've now seen that derivative has to do with this instantaneous rate of change that we've looked at in previous explorations. And now this very familiar slope formula that you've worked with, and as you know, it is the average rate of change, but it is going to come into play into what we're doing today as well in this exploration. So before we actually look at the definition of the derivative, let's get into where it's coming from. Let's talk about where the definition comes from and why it is what it's going to be. Okay, suppose that we are just starting with a point, x, f of x, standard point on a graph. And now we're going to add in another point along the graph. It's not the same x value, it's some other x value, h distance away from the original one. Right? So here we're going to assume that h is just some positive constant. Maybe it's 1, maybe it's 5, maybe it's 1 million. It's just some positive constant length, right? So this will be the x value of this second point that we're going to get somewhere along here, and then a given y value. So what is this x value here of the second point that we're going to be creating? And that point would be x plus h, because you're that h distance away from the original point. And so if we have the function value associated with that point, here it is. Now, what will be this function value? So then that's f of x plus h. So the y values are depending on the x's, just like normal. Nothing crazy here, just maybe slightly different notation than what you've seen in slope formula. Okay, now moving forward a little bit more. Now we've looked at slope before along linear functions, right? So there's a line between those points, and we're going to try and find the slope between those. Your good old familiar slope formula, change in y's divided by the changes in x's, is this guy. But suppose that now we're not going to use those labels, x1, x2, y1, y2. Let's use the labels on this graph that we've been creating, on the axes, to write this rate of change formula, to rewrite it using these values. So what would end up in this first position here? Instead of y2, if we're just following along that format, then what's going to end up here? That would be your f of x plus h, your y coordinate, but the second one, you could actually flip it. It doesn't matter which one you call 2 or 1, but you just have to be consistent, as you know. What would be in this second place? It would be minus f of x. It's the output of the first point that you have, right? So then the denominator, just following along, would be x plus h, your x value, which is this whole expression of the same point that's associated with the f of x plus h, and then minus your first x point, which here is just represented by x. Okay, so now we've rewritten slope formula in this way, which is the same thing. It's still an average rate of change between these 2 points. We're just using notation that's not y2, for example. We're using f of x plus h. All right, moving forward, there's our average rate of change. Now we're going to be looking for instantaneous rate of change. That's really the whole driving point of what we've been looking at in exploration so far, this idea of instantaneous rate of change. And it has something to do with this slope formula. Here is the definition for it. F prime of x, this is the symbol for a derivative, equals a limiting definition of that slope formula. So it is the average rate of change, but we're applying a limit on it for when h approaches 0. Right? Now this is a really interesting thing, which we will explore in a moment. Notice the only difference here is that you can do a little bit of simplifying in the denominator. Since there's an x and then a minus x, those will zero out. So it's really just h in the denominator. Okay, so then why is instantaneous rate of change a limit definition? Why is that? Let's explore that a little further. All right, this is the same image just scooched a little bit. So here's where we started. We had these two separate points, the x and then the one that's a little bit further, x plus h away. We have our limit definition for instantaneous rate of change for the derivative. Now watch what happens here. Suppose that we start with this arbitrary length of h. Well, the limit is h is approaching 0. Maybe this is h is 10. Well, then h is 7. We're approaching 0. H is 3. H equals 1, and so on. Well, if we're saying that h is approaching 0, why can't we just apply the limit when h is 0, h equals 0? Because then we don't have these 2 points anymore. If h is 0, then we're really just dealing with x, the original point, which if that's the point of interest, because we're getting closer and closer to it, why don't we just automatically in this definition put in h equals 0? So the problem with that is that you would get an undefined result, right, if h was 0. So we can approach 0, get infinitely close to 0, but we can't have 0 itself, otherwise it's undefined. So here's the definition in the pre-reading for this exploration. The derivative definition, you've just seen it, represents the instantaneous rate of change. And note here, the derivative of a function is also a function. And we can use this derivative to evaluate at certain domain values, which we'll do a little bit later. A little bit more with the definition in the pre-reading. Take a moment to read this. Okay, so you've read through this information here. This is a nice little image that shows all of these secant lines. These secant lines are running through an arc, hitting it at 2 different points. So those are your secant lines, average rates of change, like this point here to that point there. You can find the average rate of change or slope of this line. But as you bring, say this is the point of interest that we're approaching, as you make each of these other points from the secants closer and closer to that original one, like h is approaching 0, it's slowly becoming a tangent line. These secants are becoming the tangent line, which hits the arc at one point and then just goes off somewhere. So the tangent line hits at one single point. So the derivative of a function at a point is the slope of the tangent line that we're approaching. That's that whole idea of h getting closer to 0. We're making these lines closer and closer and closer to the tangent. Okay, a little bit more on the pre-reading is this definition here. We're going to be applying derivatives to this form of functions. Notice the important thing here is that x is not in a denominator, right? So we're not dealing with anything like that, like a rational function. We're dealing with a coefficient of x, just a constant, x with an exponent. There's a lot more in calculus, which gets fun, but we in this course will only be doing a certain number of functions, not all of the array that you can get. Let's try this out now with an example. Let's consider the function, a good old parent function classic, f of x equals x cubed. Now here's the definition of the derivative, the limit definition. Let's apply this definition to f of x equals x cubed. Here's what we're going to get. Notice the substitution. F of x is just the original function, right? F of x is x cubed, so this f of x is just the minus x cubed. Now f of x plus h, that has substitution, where x plus h is being substituted in place of just the x. So notice right here, it's x plus h quantity cubed. So that's that substitution of the expression. You've done things like that before. Minus the original function, x cubed, all over h. All right, we have our limit definition set up. Now, what if we were going to expand this expression a little bit, this x plus h cubed? That's stuck in parentheses with the exponent. We can expand it. If you go and do the work to expand it, it comes out to be this longer expression. So that's that cubed term. Now we can try and do a little bit more simplifying, trying to collect any like terms, general simplifying it. This is the same expression, but I did color code some pairs of like terms. X cubed and negative x cubed will cancel each other out. They're additive inverses. these are like terms, 2x squared h and x squared h. They are like terms. So we can add those two together and get 3x squared h. And the rest of the terms are the same. And now, again, we've already talked about why we can't just substitute h into the problem right now. We'll get that undefined. So instead, we can do more simplifying. No more like terms, but every term has an h. That's when factoring might be good to start looking for. You can factor an h out of each of the expressions in the numerator, and then you have a factor of h divide out by the factor of h in the denominator, which simplifies to just this expression here. And now that we have a simplified expression, if we substitute h in, it's not undefined, so we can plug h equals 0 in now that we've simplified our limit definition. And these terms zero out, 0, 0, 0, and 3x squared remains. So what we found is that the derivative of this cubic function is 3x squared. That's its derivative. All right, great. We have found a derivative. Well, what is that even good for? What's the point of finding a derivative? Quick exercise to take a look at what we can do with the derivative and what it's telling us. So we just found the derivative of x cubed. We're going to use that result to find the instantaneous rate of change at specific domain values. So let's say that we want to find the instantaneous rate of change when x is 0. What would f prime of 0 be? It would be 0. Simple substitution. Take your derivative, substitute 0 in for x, you get 0 out. Do these next 3 domain values. Okay, so again, each of them just using the derivative formula. You take 1, substitute it in, -1, substitute it in, 3, substitute it in, and we get these values. Again, great. So we're able to use the derivative formula to find instantaneous rate of change at specific points. Not average rate of change anymore. Now it's instantaneous. So one more closer look at these. What does this mean graphically? What's happening? Well, here is your parent function, x cubed. And let's take a look at when x is 0. So if x is 0, this point right here, the derivative has a value of 0. Kind of going back to that definition of secant lines becoming the tangent line. The tangent line when x is 0 is right here. It changes concavity, the curve, from curving this direction to curving upwards that direction. But this part is right where that tangent line would be. And what is the slope of that line? The slope is 0, so that's why the derivative is 0. Here's another one that's a little bit more interesting. When x is 1, so we're going to do this one. If x is 1, the derivative of the function at 1 is 3. Well, that means that the tangent line, when x is 1, that tangent line to the curve, has a slope of 3. And you can check it out and kind of see it here. If we go up 1, 2, 3, over 1, kind of do your rise over run for slope, that has a slope of 3. So that's pretty cool. When x is -1, it'll have the same thing. It happens to be the same slope. That's because this is an odd function. And then f prime of 3 has a slope, or an instantaneous rate of change, of 27. That's, if you think about it, how this parent function is shaped, 3, it's going to be pretty steep, that curved portion way up there. So it has a pretty high value for the derivative. And that is using the derivative, well, finding the derivative and then using it to find these instantaneous rates of change at particular domain values. Pretty cool introduction to calculus.